Everybody there?
So sorry if we don't have a camera pointed away from the screen, which would give you a more normal speaker experience, but hopefully you can see with the camera here. We have both a room full of students and researchers here at UW, as well as other folks joining online. We're really happy to have you here. So for everyone else, our guest today is Sean Taylor. Sean is very well known kind of in industrial data science circles, with kind of prominent work at Facebook and Lyft and other places. And he's currently chief scientist at Motif Analytics, where I don't know if he'll get to talk about it much today. They're doing really interesting work on sequence analysis and visualization. So lots of projects that overlap with many of the interests here in the room. One of the things Sean is also really well known for is bringing ideas from causal inference, particularly into industrial settings, something I'm really excited to hear about today. So with that, Sean, thanks again for joining us. The floor is yours.
Yeah, thanks, Jeff. Thanks for the invitation. Really excited to kind of talk to this group, and I hope it stimulates some discussion and feedback for me and these ideas. These are things that have been kicking around in my head for the last few months and years, actually. And so just to give you a little bit of more background on kind of where I'm coming from, is I'm formerly an academic. I did a PhD. I still try to actively publish now and again, but I'm now firmly in this kind of like, I'm an industry person and I just work on practical problems. And so I've been do a little soul searching on like, what do I have to talk about with an academic audience these days? And usually I think it's kind of like a perspective on like, what are people really doing in the real world? Like what are we doing at companies, and how does it relate to what you do in research, and how can I kind of like formalize those ideas and formalize what we're doing? And so you'll see a little bit of like just kind of theorizing about what are people actually doing in practice, and maybe that will help you realize like some ideas for applications for work that you want to work on. But it really just to like, I'm not an academic and I don't have really rigorous ideas or time to do full literature reviews. So if these ideas seem like stuff that you've come across already or that you feel quite bored by, I'd love to hear that too. Or if there's a paper that already says all these ideas, I'd love to hear about that as well. But I do think that like it's valuable to, in general, just kind of share this in this direction from a company, from somebody who's like worked on many different projects at companies. And so I hope that that's something that you find valuable. And in particular, I have been this kind of proponent at companies of formalizing problems as causal inference problems and trying to kind of treat them in a kind of rigorous way from a causality standpoint, because I think it's very beneficial for people to do that in as much as it helps solidify ideas and helps put them on the right track to get a good result. So I don't think of causal inference as like a kind of purity religious thing, but more of it's the right tool for the job that most people have. And so I've been trying to evangelize these ideas for a long time. And part of that means trying to meet people where they are and figuring out like, what do they really need? And in other cases where I'm trying to sell them a product that they don't need, and maybe try to tell them to do something else. And so you'll see a little bit of like hand-wringing about that as well. So first thing I'm going to talk about is I think of almost everything as an estimation problem. I am not a statistician by training, but I have become a statistician through practice. And so I think of everything as kind of like there's a number that you'd like to know, and if you knew it, that your life would be a lot easier. And so that's kind of like the perspective that I bring. And a lot of the numbers that you want to know are causal quantities of interest rather than just like, accounting something or computing a rate or something like that. Often the numbers are not directly observable from the data and need to be modeled in order to produce numbers that are useful. And so when you estimate things, you tend to live in bias variance trade-off land, where you can end up with two different kinds of estimation problems. And I'll talk about when we would expect to see one versus the other. And it really does matter because it affects like when you care about different kinds of causal inference ideas. And then finally, the thing that I ended up kind of converging on, and part of the reason why I work on an analytics startup right now, is that I think one of the most interesting things that ends up happening in a company is that there's all these kind of like really rigorously formalizable ideas around causal inference that really tend to gravitate toward interventions and running experiments. And I've been an experimentalist for most of my career, and I try to tell people all the time, like, we should just be running an experiment and collecting that kind of data. And now I'm trying to build a product for people who often can't or won't run experiments. And so I'm trying to square the circle there and say like, well, what value am I providing? And I think it ultimately boils down to a form of creativity, or and in science we just call this like theorizing, like creating theory from data and how we go from observations about the world and into hypotheses about causation that we can test is really top of mind for me these days. So you'll see some ideas about that. Okay, so this is my I have to evangelize this even before I evangelize causal inference. It's just that everything is an estimation problem, and so that often things that don't look like estimation problems really are ones. And I'm trying to kind of help people in analytics land start to think this way. Is that usually there's just some kind of number that you want to know, and you have to use numbers that you already do know in order to find that number. And it's a super simple idea, but this is something that is a ubiquitous thing that people are doing in practice. They just don't kind of frame it this way. And the machine learning people fitting supervised learning models think about things this way, but don't think about it as estimation. And the people in analytics land just count things, and they don't think about it as this thing either. And so I sort of am constantly trying to figure out, okay, I can make your problem into this problem, and then I know how to think about it. So why is this a useful way to think about things? Is that it has a kind of natural path to it. Like this is the way that everyone's thinking about, okay, how do I improve estimation? Well, I have a set of things that I have to do. I have to do computation, so I need to think about what language am I going to be programming in, and what packages am I going to be using, and what hyperparameters am I going to be using. And I think the real galaxy brain stuff is when people start to think, oh, I need better data, or I need to evaluate this model in a better way. That's where I tend to push people toward. But then finally at the end of all this journey of getting a better model, they realize that they have to get something done at a company and make the company better in some way in order to justify their job. And that's the part where I think the causality really comes in, is that what is this model really going to do? What are you going to do as a result of this model? And should what you're going to be doing really just be part of the model to begin with, rather than something that you do after the model's already been fit? So just a kind of quick canonical example is almost everybody at a company has worked on something like churn prediction at some point. It's very common to say oh, well, we'll just I know how to build a classifier because I'm really good at machine learning. So I'm going to take all my company's data and train the best damn user canceling account prediction model of all time. And that's going to make the business better in some way. And it's not the most unreasonable idea in the world, but the problem with this model is that it doesn't include any intervention capability. So it's sort of you predict people are going to leave, and then you just watch them leave. And that's really not kind of in the spirit of business. Is that really you should be thinking about, okay, what am I going to do about it if I think that they're going to leave? And if you know that in advance, then that should become part of the model. And this is this seems really silly, a thing to kind of just nudge people toward, is add another feature to your model. But I think it's really powerful, important point is that there's some kinds of features that are interventional features that we have control over, and some that we don't. And that the ones that you have control over are almost the most important ones to be putting into the model, not the ones that are good predictors. The ones that you have control over are the ones that are going to dictate what you would like to be doing at the end of the day. And so if you can put them in the model, that you'll have a more useful model for the kinds of problems that you're actually facing in practice. So I call this putting yourself into the model, or admitting that you have control over the system that you're operating in, rather than a passive observer of it who will just watch everybody leave after you predict that they're going to cancel their account. So once you add a single binary interventional variable to that conditional expectation model, you have this very, very common in practice at places like Lyft and Facebook, heterogeneous treatment effect model. And these are economists love these, and most of these methodologies are invented by people in econometrics. And that what's great about a heterogeneous treatment effect model is that it helps us estimate the people for whom a treatment would be most effective. And if your treatment is expensive in some way, say giving people a discount or a coupon or some kind of costly intervention, then this allows you to really carefully target that intervention in a way that's most cost effective. So this is there's an entire team of people at Lyft who decide which drivers get bonuses and which riders get coupons, and they're all based on a technology like this. And it basically boils down to that the model needs to have special features that predict response to the treatment and or the effect of the treatment itself, but then broken up into this very high dimensional space of all the possible things that we might know about a user in advance before dispersing a coupon. This also happens in I mean, it's kind of sad that there's all these optimizations, but things should you get a user if a user complains, should you get a real person on the phone to talk to about your ride being canceled or something like that. It's like, you can decide whether that's worth it or not, whether that user is going to like continue using the service after that, if they did the call or not. And if you have an estimate of that, then you can figure out whether this like costly thing that you can do is like worth it for business reasons. Okay, so we're going to fit models. We know that they're going to have some variables we can control, some variables that we can't control, but we still need to fit models because we need to have a model that can tell us the answer to the queries that we're going to be giving it. Two kinds of estimation problems that statisticians think about all the time are variance problems and bias problems. And this is just like a strict dichotomization of the mean squared error of an estimate. So it has to come from one of these two places. There's another kind of error, but it's not really relevant to what we're talking about today. So we have these variance problems which go away when you have more data. And this is like, or you have better models. And this is the one that everyone loves to think about and talk about because it's like really easy to reason about. It's like, oh, just like I will get more data and my model will be better. And then my business problem will be solved, or I'll like be more sophisticated about modeling the data that I have. Bias problems are much more pernicious because in bias problems, you often don't even know if you have a bias problem. It's sort of like something that you just have to believe that you do. And the data won't tell you that you have a bias problem on its own. You have to have like other assumptions or some source of like other domain knowledge that tells you that you have a bias problem. So bias problems occur when most common is in survey sampling. Everyone knows this one. Like you did a survey and like, most people are going to vote for this guy. And then like what ends up happening isn't exactly that. And then you're like, oh, well, maybe that survey wasn't surveying people that are representative of the voters. And so this is a representation problem. It also occurs when the data are confounded in some way. And so I'm sure you've all come across like Simpson's paradox type problems. And that's just like a very special case of a more general concept of that, like, the data that you have collected have a correlation that's different than the correlation that we observe in practice, particularly in the face of interventions. And so bias problems often, they just require like human thought and processing in order to solve. They like sort of like need a human in the loop to even know that there could be a bias problem in order to like to detect them. But they actually can be solved quite easily through randomized interventions. And so there's this like kind of like this, the solution is actually quite easy for bias problems in a lot of cases. And so like that is what I've been gravitating toward in my whole career. It's just like, let's just solve it through interventions. And you'll see that like in practice, companies really do that because it's really easy to collect new data. And this is a huge difference between an academic setting and an industry setting. In an industry setting, if you want more data, it's very easy to get it. And in fact, like a whole day passes by and you have a new data set. And that's very different than like a world where you have to kind of like go and like beg, borrow, and steal to get data. So like my perspective is very much informed by the data collection is cheap and we should try to get the data that we need for the problem that we have. Okay, so we've got bias problems and variance problems. And how do we solve them? Well, the variance problems are solved when we just like, tune the XGBoost model better. And I think this is the one that everyone really likes the solution to because it's something that you just like go and, you do all the stuff that you were trained to do in your intro data science and machine learning classes. And so it's really fun for people to work on variance problems. Bias problems are solved if you know this other thing, which is the probability of that should say P of A given X. I changed my notation at some point in these slides. So if I knew how action was assigned based on X, then the bias problem is solved because I know this correlation. And this basically requires me to know how all the users in the past got their coupons. And if I knew how they got their coupons, then I'd be fine. And in particular, the special case where the coupons were just randomly assigned with 50% probability would be the ideal case where that P of A given X would just be equal to 0.5 as a constant. And then there'd be no confounding in this data set. And I could pretend like all I have are variance problems. So the case where this probability is like a really special case and it's a really nice one. And it happens very easily in the case where you have controlled the intervention mechanism. And that's exactly what we do at companies is like we intervene and we log how we intervene and how we chose to do it. And so it's a little more complicated than in practice, but like knowing that probability of like what action was chosen given what particular state of the world we were in is like kind of the key. I'm going to pause there for a second before I keep moving. Any questions or comments so far? All right, I hope this isn't too basic. I think that this is like intro causal inference stuff, but I just want to get it fixed terms and everything. Okay. Okay, so here's the flow chart for like how to solve an estimation problem. You have a bottleneck. It's either variance or bias. If you tell me about your problem, I could probably tell you which one it is. But like, there's some like empiricism here too. Like it could be that like you can check and see, but in general, like you have to think about what are you trying to solve, and usually it's pretty clear answer. If you have a variance problem, you can acquire more data, or you can improve your outcome model with like more features or better pooling of information. If you have a bias problem, you can improve your treatment model, that probability that I was describing of like what action was chosen given what particular state of the world we were in. Or you just intervene randomly and choose that, make that model true by definition by doing it the way that you have chosen. And that is like basically where I ended up in my career after like, I joined Facebook in 2012. I stayed there for 7 years. So like over the course of the 7 years, it's just like, we're just going to run experiments for anything that we feel like we have any bias in. And then like, that will be the solution. So I became an experimentalist just because I liked solving estimation problems in the most efficient way possible. And I walked down the flow chart and it was like, okay, this is the solution. So here's like kind of like one conception of what happens when interventions get really cheap, is that you sort of like can estimate more causal effects with more precision, more cheaply. And so I kind of walking like left to right on this curve through my career, where you have this like artisanal causal inference is what I call like what people in like often in economic studies do, where they like, carefully collect the data and like verify the assumptions and then do a bunch of robustness checks. And it's really hard and it takes a lot of time, and people still doubt your result because you're relying on some kind of careful strategy for estimation. And then what I did in grad school was like go partner with the company and we'll just go run the experiment. And then when I moved to a company where I could run my own experiments, it's just like, just run as many as you want and don't think too hard about like how much they cost, because there's no real fixed cost to them anymore. And then when I got to Lyft, it was like, actually, experiments are an algorithm, and that we don't really even need to think hard about, like, we can estimate like many kinds of causal effects, very, very cheaply. And this is like really high bandwidth experimentation that most companies that are doing like algorithmic policies are engaging in on some, in some level, whether they like it or not, because this is the most efficient way to accumulate knowledge about what to do with with decision making that's that really high volume, like as like for instance through like Lyft's pricing algorithm or coupon algorithm. So I found it really interesting to think about like what happens when experiments are like basically free. Like what is like the difference in the world compared to the world where like experiments are really expensive. And I thought like what ends up happening is that you end up in this optimization land where like actually you don't care about the estimates anymore. It's kind of interesting. Like once you can estimate something cheaply, it's like doesn't become that interesting to look at the estimates anymore. And the interesting thing is just using that knowledge to optimize some system. And so you're frequently living in a world where you are trying to decide on whether you're exploring or exploiting. And there's just some fundamental constraints there. Like, are you designing a fully random experiment where you're trying to learn the most general possible model? Or are you really honing in on the area of the distribution that provides like, the most benefit to the system in some way? Then there's this like objective function definition thing, which is every company I've been at has spent a really long time hand-wringing about what are we really optimizing for in the first place. So you have this like other kind of uncertainty that then ends up popping in, which is like not anything that you can possibly estimate, but actually like a choice that you have to make about what your priorities are for your company. So Lyft, for instance, would have like this three-way utility split. We had to split a pie between riders and drivers and then the company. So there'd be like profit, there'd be like rider surplus, and there'd be driver surplus. And depending on how you care about those things, you would do very different things in all of your algorithms. And choosing between those trade-offs is like a really important part of the business, but it's not related to estimation at all. It's kind of one of these things where like you can't actually estimate it. And then finally, the third thing is that like, what do you have available as interventions in the first place is like the thing that I'm now currently most interested in, which is like, it's kind of a meta problem. It's like, if you zoomed out of, like, what experiments are even available to run? I'll give you an example of that is like at Lyft, there's an easy way to say like, okay, there's like a 10% off coupon, a 15% off coupon, a 20% off coupon, but like you could come up with more complicated versions of a coupon, right? Like maybe you have to take 3 rides and then the 4th one is 20% off, or you have to take, you ride 10 times this week and then next week you get a free ride. So you can invent new treatments and they're all going to have a different effect, and there might be different, they might some of them might be more interesting or useful to the system than others. And so like, where do those come from isn't something that you can answer with data. It's something that you have to kind of like come up with through human domain knowledge and theory. So these are the 3 like problems that remain when interventions are basically like free or so cheap that you don't think about estimation problems as being a problem anymore. All right, so I call this the experimenter's 3 tensor. I just totally made up this terminology, but it's like my mental model for what we're doing. We're running experiments in practice, is that there's like this 3-dimensional cube that has different cell values in it. And so the contexts are along 1 dimension. This is like the X variables, like what you know about a user or a situation in advance. And then we have the action space, which are like our various things that we could do in that particular situation, like give a coupon or not, or charge a high price, or charge a 5% markup or a 4% markup or a 9% markup or whatever. And then we have the outcome space, which are like what happens after that treatment has been applied or that action has been taken. And this can be like, a variety of things. Usually it's pretty high dimensional. And so like knowing basically in this context, if I do A, this vector of outcomes will obtain is kind of like a very useful thing to have known. And so like filling in entries in this tensor is kind of the name of the game for a lot of companies. It's like if you had like data in every cell of this tensor, then you would know what to do, because you would just like pick the one that maximizes some objective that you have. And so like a lot of the free cheapness of experimentation basically ends up being wasted because we have to spread it uniformly across this matrix in some way. We have to like choose where we want to be doing the experimentation. And I just want to point out that the most common thing that people do at companies is just a simple A/B test where they actually don't condition on any context at all. And they collect data from like an A condition and a B condition, which are just a binary action space. And they look at a variety of outcomes for A/B tests usually, but it's a special case of the experimenter's 3 tensor is like the A/B test. And you're probably familiar with multi-arm bandits, which is just like high dimensional action space. And they have like kind of heterogeneous versions of the multi-arm bandits where you would go the other direction. And then the HDE models that I described to you earlier were just like, binary treatment, but many dimensional context. So it all kind of like fits in here. There's some version of most kind of causal inference problems at companies that like can be kind of shoehorned into this 3 tensor matrix in some way. Okay, so we have this tensor. We're going to like use interventions. Interventions just mean effectively that I get to sample points in this tensor any way that I want, because I can choose. So I get to like choose how, like in context X, which action am I going to take? And I'm going to log a little entry of like what outcomes obtained. So I get to choose. And so I get to like basically sample from this tensor any way that I want. That's what interventions mean in my head. So I'll go back to our flowchart. And so you take the bias path of like, I'm going to have no bias because I'm going to intervene in a way that prevents me from having bias, because I decouple the state from the action space by applying some randomization while I'm sampling. And then you end up with a variance problem again. So you sort of like you've solved your bias problem and now you have variance problem. And so like a lot of work at companies now is like, oh, I don't have bias problems anymore. I just have variance problems, is to like figure out how to acquire more data, which is like essentially, from my perspective, trying to encourage more experimentation at the company, like more randomization, like actually more exploration and adding more randomness to the system, because it encourages like more entries in that like tensor to be filled out, which is interesting in the sense of like that experiments form a kind of pool of knowledge that you have available for future problems. And so one example of this at Lyft was like we had this ongoing price experiment, which is like all 10% of Lyft sessions have randomness added to the price. And it's been running for like 3 or 4 years now. So there's just like this really rich data set of like, every situation possible, every price that's reasonably possible has been charged. And so there's a really like kind of strong corpus of data available for answering questions about pricing counterfactuals. Sorry, I got a question. I'm going to take it.
Yeah, thank you. No, this is super interesting. And my question is, there's also another axis, I think, especially in this context in industry, the axis of time. Like the moment you start the experiment, those axes, right? Like the users are changing, and there might be even other experiments happening at the same time. So I'm curious, how do you handle that dynamic nature of the
Right.
problem?
Yeah, it's a great question. I personally think of that as just a context variable, but that means that like there's like a staleness to the samples, like and ultimately time is just a special covariate where you want to do some kind of pooling over time. Like if you only used yesterday's data to predict the future, it would be really wasteful because there'd be like data from a week or 4 weeks ago that was still relevant. But if you go too far back in time, then it's not super relevant at all anymore. And we had like, I remember doing, during COVID, we ran this, like that pricing experiment I was telling you about, we could analyze it like week by week at Lyft and show how do people's price sensitivity change, like, over time. And it does change quite substantially. And it means that you are effectively performing an extrapolation in the time dimension, in addition to all the other dimensions that you're estimating over too. So, but I don't have a good answer to like most people don't think about that extrapolation error when they think about experimentation estimates at all. But it's an excellent observation.
So Sean, can I follow up with some questions? Because I was thinking along some similar lines here, and just wondering, kind of in the logistics of running these experiments. So one, is it really true that it's that cheap? Like, could you have interventions that are costly? Is it once you have a large enough user base, you can bound it and still get the data you need, as one way to avoiding that? And I guess my second follow-on, which may or may not intersect with that, then becomes also, if you're running these many experiments, do you have to worry about interaction effects across these different experiments if they're co-running, or do you really try and segment, the user base that you're running these experiments on such that they don't overlap?
Right. Yeah, they're both good questions. To the first one, yeah, you're always sample size constrained, and yeah, like Lyft is like 2-3 orders of magnitude less interaction data than a place like Facebook. So like a place like Facebook can do very data intensive experimentation and modeling, and I think of it as that they can search a higher dimensional search space faster because they have more samples. So that's a good way to think about it. And yeah, there's some fundamental information theoretic constraint, just like that you have only so many samples to work with, and that's why the explore exploit becomes very important, is that if you're exploring like too uniformly, and you're focusing your sampling on regions of the space that you're probably not going to operate in. And so like that efficiency of the sampling boils down to whether you're like using your samples where they're most valuable for pivotal decisions, like a user that you'll never give a coupon to. There's no sense in like experimenting with giving them a coupon, like if they have very low incrementality, but ones that are like on the borderline are much more valuable samples. And then the question about the interaction of the experiments, yes, they do interact. I found that I ended up theorizing this a little bit. It's like at Facebook, is assumed that they almost never interact because product surfaces are reasonably orthogonal to one another. So like a team that works on the groups product at Facebook and the Messenger product and the Instagram product all like don't need to care too much about each other, or they would view that as second order. And it's been studied, like they will like run, a correlation analysis, like try to see if the interaction effects between those experiments do occur. And I even like had somebody do that on my team when I was there, and we ended up not finding anything. But at Lyft, it really does matter because all of those experiments operate through similar mechanisms. So like at Lyft, like many of the experiments operate through either price or wait time experience for people. So like if you change something about the system, there's a kind of causal bottleneck of like that they will try to use the same levers in people's brains, like they feel like they had a better experience because it was cheaper or because the time spent waiting was less. And those are the only real ways to make a Lyft ride better. And so like everybody's trying to improve through these same mechanisms at the same time. And so the spillovers are much more or interaction effects are much more plausible in that setting. So I think the answer to that one is it depends. And at a place like Lyft, the experiments are much more carefully kind of coordinated than they were at Facebook.
Thanks.
All right. I just want to mention that like modeling does provide this like improved outcome model thing is kind of a thing that a lot of people tech companies focus on. We call it variance reduction, but variance reduction is a really hot topic in experimentation because you get like a free, by knowing the outcome model, like having a better predictive model of users, you get like free sample size because you get more signal to noise ratio from your experiment. So if you know that like a lot about what a user is going to do tomorrow, then your experiment is more precise. Like you have lower variance of the error term. So this is one of the few times when you can tell people to like spend a bunch of time like training and tuning some predictive model. It's like it actually does help with experiments in this other way, but you have to have an unbiased estimate before you can start thinking about doing that. Okay. All right. So we have good estimation. Now, what comes next is it's obviously optimization. You're a company. You're trying to optimize some objective function, and so I think of as data science as two steps: estimation step and argmax step. So estimation step is build this model. Optimization step is the argmax step, where you pick the best action. So this first thing is just choosing the best action for state X. The second thing is like what I would call policy optimization, where I am finding a function f that maps context into the best thing to do in that context. And this is like algorithmic design. I mean, this is the space that like everybody, like all the people I work with at Lyft work on designing F. It's like their whole life is like, what should F be for all these different policies? And it's really quite rich. Like it's not just like coupons. There's the pricing algorithm, which chooses a price, and it's not just one price. It would be price for a shared ride, a like standard ride, a Lux ride, and then now there's like different prices for different wait times as well. So there's like this vector of prices, and then there's another F at Lyft for the dispatch algorithm, which matches riders to drivers. So like A in that context is like a big matrix of like which riders are available and which drivers are available and which ones get routed to one another. And then there's a big function E that like evaluates like how much welfare we'll obtain in that like next 3 minutes from like having done that matching allocation. And then you are trying to argmax over like Fs that map people's positions and times of their requests into like a big allocation matrix. So you can do really complicated things with this setup, and it doesn't require a lot of extensions really. And F is inherently very high dimensional. So, and it's harder to evaluate F than it is to evaluate that conditional expectation function, because often your samples don't really correspond to like actions that you've taken in the past. So it's easy to evaluate an conditional expectation model, but hard to evaluate a policy. And so a lot of work basically is like what we call like counterfactual policy estimation or optimization, where you're trying to like say, oh, like if we lived in a world where we dispatch drivers in a different way, like what would happen to all the different outcomes? And that's a very common question, and it's very hard to answer. So then after you can do optimization, like there's this like next few set of questions, which are like super interesting, but mostly organizational in nature. It's like you made your model do something good. Next is like making the model not do something bad, which is like an inevitable consequence of having the model do something good is that you've chosen the wrong objective function and it starts doing something bad. And then once you know that it does bad things, like you end up in a trade-off space where you're trying to figure out, okay, like, well, how do I know how to trade off the good and the bad thing? And then finally, it's like not just one person gets to decide whether you trade off like two things in a certain way, but it's actually a group of people. So you get into you go into like political science, like from first principles at any company that's doing experiments, because like this is all really important stuff. And so I just think it's funny that like you started with like, what language should I use? And you ended up like, trying to like, build coalitions in your company so that you get the model to do the thing that you want it to do. But a really common thing to do is to like take an experiment and plot like on one axis like metric 1 and on the other axis like metric 2. And if you've run many experiments over time, what you'll tend to do is you'll see like a trade-off curve of like experiments that tend to move metric 1, which is good, also tend to move metric 2, which is bad. And like we need to come up with an exchange rate between those two things. And so like causal inference, like because causal inference work tends to imply a course of action, it also tends to have like trade-off math associated with it that people are unprepared for when they start the statistics part of it. And so it's kind of like just something that I've observed inevitably, that this is what happens because these models are designed to tell you what to do. And people don't really like being told that they're supposed to do a certain thing because it doesn't capture like some other thing that they care about. So the lessons from like my life so far as a data scientist working on causal inference is like there's optimization is a natural end state. Like no one actually cares. Like it's funny, I spent all my life in academic world like trying to estimate things so I could like publish about them, and like the number actually mattered. But now the numbers don't matter at all. I can't remember like one number from an estimate from a lift experiment that we ran. But I remember what things shipped and like what the result of them was overall. And so there's kind of like the decisions are the outcome, not the estimation. So decisions are important, policies are important, but estimates are no longer that important. They're just kind of like nuisance parameters. And there's no real theory going on in these companies like at all. Like it's just kind of like people just try lots of stuff and they just want to see what works. And so that, like there maybe like informally there's some theory going on. And I think I made my peace with like maybe that's okay, that we don't need like a whole scientific method applied to every business decision, because it's like just something that people like the theory would go stale as soon as you created it. Unlike theory about like physics and chemistry and even economics, it's just kind of like that there's not a lot of like staying power for theories in businesses. Maybe I'm wrong about that. Actually, like some of the analytics work we're doing, I hope will disprove that. But you still need human domain knowledge, and it's because you have trade-offs to guide these policy choices. And then finally, this part that I'm interested in is like developing and building like what are the interventions that you're going to try, and like what could be fixed, what could be improved. It is still something that comes from humans. And so there's this question of okay, like well, what role do humans have when you start to like you have these optimization machinery, there's a human in the loop, the human is going to like help guide it in a certain way, and it's going to be through like what are we going to make available for it to do. Okay, so I'm running a little slow on time, but I'm making this kind of scientific knowledge loop point here, which is that like the idealized scientific process is that you have hypotheses come from like some body of knowledge you've created about the world, and then you go through this loop of like estimating things and go back into scientific knowledge. At a company, what I noticed was that like we didn't actually do that. We just kind of like tried stuff. There was like this missing part of the loop where like what process are we using to decide what to build next, or like what should be tried? And I don't know if there's a lot of formalizations of that just yet. So I tried to do that myself. This is just like a first crack at that, but roughly like you can think of causes and effects as being like known or unknown, or like kind of something that you have theorized about or not theorized about. And if you have it in this 2x2 like this, then you have kind of the known cause, known effect world is a hypothesis testing world where you are choosing to evaluate like whether these two things that you're hypothesized, the hypothesized relationship holds. So this is kind of like an A/B test. Like if users had this new feature, I think that they would be happier and use our product more. But these like off diagonal quadrants, the characterization and the explanation ones are the ones where you're like generating hypotheses, like, oh, I did a thing and like there were some consequences I didn't think about, and I want to like figure out what those were. And that's kind of theory building. It's like thinking about like what could have been the consequences of a thing that we launched before I even looked at the data. And then this explanation quadrant is like something. I want to find the kinds of things that make good things happen, or the kinds of things that make bad things happen. What kinds of things cause users to be happier? What kinds of things cause users to leave and never consider using my product again? And what are they? And how do I prevent them? And that's the world that people in analytics live in, is that they have these like kind of ill-posed questions. They're not formal statistical estimators where you're like, oh, there's just a number, and if I knew it, then the answer would be pretty clear. It's actually like, I don't know which of many, many possible things this thing could be, and I need to search and build some intuition for it. And it's going to be ultimately something that might live in my head rather than in a particular model. So if I draw a lot of causal DAGs because that's how I was trained. And so these two kinds of DAGs look like this, where there's the characterization DAG is you have like an action, and then there's like this huge set of possible consequences from it. And then you have this explanation DAG where there's many possible causes of an effect, and you would like to know which ones are like the most important ones. And it could be more than one of them. And this is sometimes people call this polycausal, where there's like for any outcome that occurs, like often many things contributed to it and like in concert with one another. And so it could be even complicated, and then it's just one or two of these things. It might not be sparse. And I lately have been more interested in the second one, because I think that this is what people in product analytics think about the most, is that they are constantly trying to come up with ways to figure out how to make the product better through like unknown causes. What could I do and propose to my company tomorrow that would like make the business better in some way? And it can't be part of our already existing DAG. Like there's some things that we've already evaluated, but there's got to be some things that affect things that we haven't thought about yet. And if they didn't exist, then we would already have the model of the business, and we wouldn't even need to employ people to be looking at the data. So people in analytics world are like building theory, and they're not admitting to themselves that they're scientists who are building theory, maybe, but they are. At least that's kind of my current conception of what's going on. And I really like this. This is this plot from this guy, Seth Roberts, who, if you look him up, he might sound like kind of a crank. He was a professor at Berkeley, who I used to read his blog really all the time in grad school, and he would do these self-experiments. So he would kind of like just decide he wasn't sleeping well, and then decide to try like 10 different things in the next week to see if it could like improve his sleep. And he would admit that this is not a very like rigorous evaluation of those methodologies, but that the self-experimentation could be useful for idea generation, and that like he had this theory that scientific knowledge has this kind of like bursty pattern of that, like sometimes idea generation is so good that it's so much more valuable than confirming or disconfirming an existing theory, that we should be focusing some attention on that part of things. And now I tend to agree with that, because I have a company that's motivated to do that for people. But if you have a theory and you confirm it, that's very low value information, right? Because you already convince yourself that theory is true. And so when you confirm it, it's just like, oh, it's like marginal. It's like, oh, I feel more confident about a thing I already knew. If you disconfirm a thing, yeah, that's great. It's like, okay, this thing that we thought we knew isn't true. But even more valuable is like a thing that we hadn't even thought of to confirm or disconfirm yet. Let's like throw that out there. And then if that thing ever gets confirmed, it has this option value of being like an incredibly valuable discovery. And so we need to figure out like, how do we aid people in doing this idea generation phase, and what does that really take? And I think it basically boils down to observations. So just a quick aside here, where do actions come from? And if you think about your causal inference person, like this is like a really existential question. It's like, I'm doing causal inference. There's a thing in my model that I'm saying is a cause. Like where did the cause even come from? Where do causes come from in the first place? And they're designs, right? They're things that people choose and make and manufacture or configure. And so I started to think about, where do the actions come from? And I basically boil it down to like, there's human design and machine design actions. And the kind of current thing that people mostly do is human designed actions, where most experiments, like every pill, there's some drug discovery stuff, but like, mainly like medical treatments or things like that, or like humans spend a lot of time thinking and they come up with an idea, and then we're going to test it. And so human intelligence plays an important role there. There's also this potential for for machines to design actions where they just like search a space and come up with promising candidates for us to test without us having humans in the loop at all. And I think this is kind of what's happening when you have these high dimensional experimentation frameworks, where you're like really trying to figure out which is the best of many possible configurations, some of which you haven't even tested yet. So machine design experiments can come about in the following way. So we used to fit at Lyft these things called response surfaces. So our primetime algorithm at Lyft had like two parameters, just like two continuous numbers. And when you set them to different settings, you would get this like surface of possible, let's say this was like Lyft revenue or something like that. So the hills are good values where Lyft makes more revenue when set point is at a high level and KI is at a high level. And fitting this response surface has an interesting implication, is that it can make a prediction about points on the response surface that you have not sampled yet. So there's like points somewhere. We have done a very efficient exploration for these 2 points, but if the space were higher dimensional, then there's points that you could like extrapolate to and say like, what would happen if we were in that point? And that's something a machine could do, is it could like draw from that distribution and like find that point. and tell you, hey, you should go evaluate that point and tell me if it's any good or not. And that's something that people in the Gaussian process modeling world are really interested in these days. It's like high dimensional Gaussian processes. And it's pretty interesting these days with embeddings and things like large language models, is that like a high dimensional point could be anything. It could be an image, it could be a block of text. It could be like, so like the idea of synthesizing a new treatment from thin air is actually not too far-fetched at this point. But that's a bit of an aside. I think machine designed actions are really exciting, and there's also like protein folding and drug discovery and all that stuff, and we should be paying attention to it. But I want to set that to the side and say, like, I still think humans play an important role. And I'll give an example of that, which is I worked on at Facebook for like a year. We had this product called stickers, and it was like we had to design and curate like a sticker pack that would go into the product and encourage people to send more messages. And we ended up having like many possible sticker packs. And so we would run an experiment where we would like randomize which pack was the default pack for a user when they showed up to Facebook Messenger. Like, what pack did you have installed on your app already? And then we could look at like which kinds of packs cause people to be more excited about sending stickers and being on the app. And we could run this like 58 arm experiment where we found out that Angry Birds is the one that causes people to want to use stickers more often. But then you could use these experimental estimates, send them to the artist team that goes and figures out which packs to make, and like have them go and like find the kinds of packs that are the most useful for people to make. So there's like this human creativity and like find me stuff that's like the stuff that works already, that I think is a really important and interesting thing that we should be thinking about. It's like, how do we stimulate creativity or help people like find the patterns that help them come up with the ideas? And this is one example of, I think, that playing out in practice. The kind of sad part about this whole exercise was it turned out that like a lot of the most persuasive packs were from company like IP, like stuff like Kung Fu Panda and Angry Birds and the Peanuts movie, like which were like expensive for Facebook to obtain. So it wasn't like, so it's just like kind of had this interesting sad part to it, was that people just like content that they've already seen before. Okay, so we're talking about where do treatments come from. Another treatment that I was thinking about that this is like a really great case study, is the Lost Cure for Scurvy. It's like a really cool essay. I highly recommend reading. The link's on the bottom. I'll send it later. Basically, at one point, by 1911, the cure for scurvy was thought to be known, which is that you had to consume lemon juice, and then if you consume lemon juice, you just like wouldn't get scurvy. And then we're like, okay, well, we go on this voyage in 1911. They went to, I think it was Antarctica, and they brought lime juice instead of lemon juice because it was cheaper. And they stored the lime juice in copper tanks. And so it still tasted like lime juice, but it deactivated the vitamin C. And then the people on this voyage in 1911, actually, like a lot of them died of scurvy despite consuming lime juice. And so then they were like, man, this cure for scurvy doesn't even work anymore. And it was, it kind of made sense that like they weren't evaluating lime juice very stringently anymore, because most of the ship voyages were very short by 1911. So it used to be the long ones were the ones where people would die of scurvy. They didn't have long ones anymore. They switched over to lime juice. Lime juice didn't actually work, but they didn't figure it out until they had this one particular trip. And it's because of this causal DAG here, which is like lime juice does cause citrus flavor, but it doesn't cause vitamin C levels. And vitamin C levels are the only thing that actually cure scurvy. So they didn't know the mechanism of action of the treatment. They only knew that the treatment worked. And so when something unobserved about the treatment stopped existing, that the cause didn't work anymore. And the really interesting thing about this story is 1912 is when they isolated vitamin C as a chemical. So it wasn't even possible to know that this was the mechanism of action for their cure until a year later. So there's just like this missing scientific observation. It's like an unknown downstream effect of the treatment, and the mechanism being unobservable makes it sort of like very difficult to know that when you switch to a new treatment that it's going to work. And a lot of like treatment design basically boils down to knowing the mechanism. And you think about like, how do people design treatments for drugs? It's like, well, you isolate like, well, I know vitamin C prevents scurvy, so I can make a pill that has vitamin C, and then I don't even need to take a lemon juice or lime juice or any kind of juice on the trip at all. And so like you could potentially have done that, but but you have to know about vitamin C. And if you really think that like, I don't know anything about the mechanism, then you have to just run experiments, which is like the world that I come from. But if you ran only experiments here, it would be like the worst thing in the world. You'd be running experiments and like hoping that people die of scurvy so that you can detect whether a treatment is effective or not. It's like, it's just like totally nonsense. Like, it's just not an effective way to get this information. You actually like the best way to do to design a cure for scurvy is to literally just know the mechanism, not to like send a bunch of ships out with different kinds of citrus juices in different kinds of tanks or something like that. That would be crazy. So it gets to the point. It gets to the point of like that. There's some observations that are not causal, not interventions, not experiments, but that provide valuable causal information that we need to know about in order to think about what we should be doing in practice. And this is like what I perceive that people in the kind of analytics space to be doing. So how do we get these like interstitial measurements? How do we get the stuff in between the cause and the effect? Our current knowledge of the cause and the effect, there's something that happens in between that is like important for us to know because it helps us understand like why the treatment works in the first place. So what am I doing at Motif? Well, we think of modern instrumentation where we have like a logging framework on the request and the response as capturing like a really rich data set of like everything that a person, if I'm a Lyft user, my whole like experience with Lyft could be captured as a story, as a set of steps that happen. It's the server sends something to the client, the user does something on the client, sends it back to the server, and I'm like instrumenting that and I'm capturing like every step along the way. And so we can make a causal DAG of all those events if we wanted to, or we could say like, okay, well, there's these like unobserved states where the user is thinking about something, and then the user chooses to do something, and then they choose to do what they're going to do based on what they're thinking and what the server has sent back. And then we go through this kind of process in a loop. And we don't collect the U variables because those are unobserved confounders, but we do collect the A's and the Y's. So A's are actions that we took, and Y's are outcomes that we've observed. And so this is like the most like low level representation of everything that happens on like an app or a service or something like that. And so my hypothesis is that this is like, you know, the equivalent of like needing whatever lab equipment you needed to detect vitamin C. This is what you need to detect like things that affect people's behaviors and outcomes. It's like everything that happens in between. I don't know if that's true or not. It could be that everything's in the U's and that you can't control anything. But the hope is that if there's something that you can control, that it's got to be like in the A's and Y's. And so this is like just a kind of quick visualization of what can you do with sequence data. This is a case control study, and I'm not sure if you come across this methodology, but it's considered to be like a weaker form of causal evidence than an experiment, but still valid in some cases where you can't run experiments. And what do you do? You take some outcomes, like in the case of analytics, like retention or revenue, or how much time the user spends on the site, and you want to attribute that outcome to some causal factor T. I should have used A here, but I had already used it for the logging. And I want to make sure that the X's, the stuff that happened before T, are not explanations for this, like they get ruled out. And so I really need to kind of like understand the difference between these two probability distributions. But I also need another condition, which is that the X's are balanced. So it's not just the ratio of these two probability distributions. It's like I need to make sure that the X's are adjusted for. So this is like my kind of hand wavy argument that this would work, is that we're going to take two sequences. There are each of these lines. The red dot represents like a case where something like good happened. The white dot represents the case where something like not good happened. And then if I'm able to adjust for everything that happens prior to the dashed line and say like, oh, it's equal. Those two groups were at this point had the same composition. They were like, you know, the same, they were comparable. And then in between that, like that dash line and the good or bad thing happening, or the good thing happening or not happening, like something happened and it was different. And I can take that differences and I can rank them, and I can go and look at them and see like what are the potential explanations. This is the closest thing I can think of to like a mechanism in sequence data. This is like there's some paths that occur that seem to be associated with the good thing, and that could be a source of causal evidence for generating hypotheses about like what it could have been. And I just want to like point out that this methodology, like it's not taught, it wasn't taught to me, actually. I only learned about case control study after grad school, because economists who I trained with think of case control studies as like really kind of shoddy evidence. But it also is the kind of evidence that confirm that smoking causes cancer. So like it's the kind of evidence that we all have come to believe about this particular thing, where you can't like run an experiment where you force people to smoke cigarettes, but you can run a case control study and get really rigorous evidence. And they did basically this, the thing I just described, like this, they like just did that by matching people at the hospital who had similar, were both at the hospital and the same age and gender, but then differed on what happened in between, which was the smoking behavior, which is like whether they were smoking 1, 5, 15, 25, or 50 cigarettes a week. And then use this as the evidence for like, hey, the smoking is very, very strongly associated with carcinoma. And so this is why we need to worry about it. Okay. Anyway, so just to wrap up, I'm trying to advocate for like, there's this interesting step before experiments where we come up with ideas and prioritize them. And I think it's like a process that's a little under theorized and understudied. And it's theories about theory. Like, where does theory come from? Where do ideas come from? Where do people at the company that we work for like come up with the stuff that they come up with? And what would the result of more data and better tools be for doing that? I think it's really, really interesting, because it's not so formalizable as the problems that I talked about at the beginning of the talk. And just to kind of quickly wrap up, it's like I think I roughly convinced myself that these are the 3 clusters of causal inference work at companies. They're sort of like product experiments where you have low dimensional hypothesis space, interventions are available, variance reduction is important. You have this policy optimization side where you're doing like algorithmic optimization. And then you have this new thing, it's not new, but new for me to start thinking about is like, where do hypotheses even come from in the first place? And I think it's really interesting space, and I have not thought it all the way through yet. So would really love to hear your thoughts and feedback on that. All right, I'm going to stop there.